Good morning, ladies and gentlemen. Our next part of electrical circuits is going to be talking about how to solve for problems when you combine multiple resistors into a circuit. And the first type that we're going to talk about is series resistors in circuits. Okay. So what exactly does it mean to be in series? Well, if you think about the World Series of baseball, right? You play one game after another, after another, after another. And the same idea, of course, is with these light bulbs over here. We have one light bulb placed after another, after another, after another. And it doesn't even matter how I draw it. If I were to put more onto a circuit, because ultimately you have one resistor after another, after another, after another, okay? And our most easily seen example, of course, is with Christmas lights. And keep in mind what happens when you take one light bulb out of the Christmas lights. Of course, they all turn off. And it's the same idea with series circuits. If you take out one resistor, you cut the power to the rest of the bulb simply because you're turning off the circuit itself. And always keep in mind, even though I'm drawing squares for my circuit diagrams, that these are really light bulbs or resistors that are being connected together with wires. They're very malleable. And you can see that overall you have one connected to another on the other side, and eventually connected back to the battery source. And once they're all connected, we have our entire circuit loop. And as you turn the voltage higher and higher, you can see the light bulbs turning on. A better diagram will be, of course, over here. And understand that you will eventually have to build these circuits yourselves as well. So keep in mind how series circuits are created. And we can see here we have one consistent loop through the circuit. If you remove any of the light bulbs, you would break that loop. Here's a more conceptual diagram of what we're seeing. We have our battery pump, our potential difference source, which is giving a potential energy to those charges, to our positive charges as they go around. Of course, this is conventional current. This is not electron current. But the idea works similarly. And notice, as the electrons fall down the potential difference, some of that energy gets used up. Okay? So, for example, let's say I had a 10-volt battery. And when you talk about how far it falls, you can see that in this case, because the resistors are equal to each other, that they fall down in equal distance or an equal electric potential difference as they get down to the bottom. And then the battery will recycle those charges and bring them back around. So if I were to talk about the total voltage of the battery, I'll label that as just VT. Then all those voltage drops, when they're used up by the resistors, well, they all add up back to that original value. Okay, or you could write that in a more formal math way. The total voltage is simply equal to the sum of all the voltages. Okay, so I'll write the total voltage in a series circuit, Vs, is equal to the sum of all the voltages. And how does the size of the resistor relate to the voltage drop itself? Well, here's another diagram, but now we don't have equal resistors anymore. We have a 10 ohm resistor and a 30 ohm resistor. Notice the 30 ohm resistor uses up more of that potential energy. In fact, because it's 3 times larger resistance, it actually uses up 3 times more potential difference. So if I have an example, let's say I have 8 volts over here. The question is, how much voltage is used at each one? And this will end up actually being a simple ratio question where if we have x plus 3x is equal to 8 volts, we have 4x is equal to 8 volts, therefore x is equal to 2 volts. So therefore, the 30 ohm uses 6 volts, and the 10 ohm uses 2 volts. But together, they add up back to the 8 volts. So our total voltage is always going to add up, but the larger resistor uses up more of the energy. Okay? But we should also take note of what happens with the current as it goes through a series circuit. And how would we solve for the equivalent resistance? Let's go back to the original picture. Now notice, the current flow here, I. How does it compare to the current flow over here? And you notice, well, it's exactly the same. And that's because it is a chain reaction. One charge pushes the next, pushes the next, pushes the next. If you were to put in a larger resistor here that was harder to get through, and you slowed all the electrons down right here, well, that would slow down the entire chain because one can't go faster than another. It's like a tube of water, okay? One portion, the flow rate has to be exactly the same in all locations, and the current has to be exactly the same throughout this entire pipe. So understand that the total current in a series circuit, IS, okay, whether it's going through the battery or wherever it might be, is going to equal the same current at whatever location you have it, whether it's location 1, location 2, location 3. Okay, the current is I don't want to say constant, but it's the same value. I can't say constant because if I increase the resistance, the current would decrease, but it would decrease by the same amount everywhere. Let's see. So over here, I write down that the current in a series circuit is equal everywhere. But the equivalent resistance is just a fancy way of saying the total resistance in the circuit. In other words, if I took all the entire chain of resistors, if I want to replace it with just one resistor, what would the equivalent resistance of that one resistor be compared to all of it? So it's just a fancy way of saying the total resistance. And you can see that if you were to put more and more resistors into the circuit, if I put another one over here, another one over here, then eventually it would slow all those currents, slow all those charges down. So meaning that the total resistance in a series circuit is, well, you simply add them all up. Okay, R1 plus R2 plus R3. The more we put in, the higher the resistance. So in this case over here, if you take a look at this example, what's the equivalent resistance? 13 plus 10 plus 4 is simply equal to 27 ohms. Okay. Or if you happen to know that the equivalent resistance is equal to 48 ohms, and this is 13 and 20, then of course R3 would have to be 15 ohms over here. So that way the total would equal to 48. Okay, and let's talk about how we actually solve a problem here. Now we have three resistors, 3, 6, and a 9 ohm resistor connected to a 24 volt battery. And they ask us a whole bunch of questions. Now, I'm going to teach you guys an easier method of solving for this. It's called, well, simply putting everything into a chart. So let's just redraw this diagram over here. I'll use proper notation. Three ohms, 6 ohms, 9 ohms, 24 volts. I, of course, know that the 3 ohm resistor will use the least potential difference, and the 9 would use 3 times more than the 3 ohm, because it's 3 times the resistance. The chart I'm going to make is what I simply call an R, V, I, P chart. R equals V over I, and P is equal to VI. And when you make this chart, it's simply just going to be a fancy way of organizing all of our data. We have a total of 3 resistors. we have some sort of total. So if I take my information from my diagram and put it into my chart, I know I have a 3 ohm resistor, a 6 ohm resistor, and a 9 ohm resistor. And the battery is the total voltage. That's going to go right here, 24 volts. Now, let me explain the only real rules with using this chart. Whenever you're going across the chart, you're going to use V is equal to IR or P is equal to VI. Okay? So whenever you're going across the chart, you can use either of these two formulas. Whenever you're going up and down the columns, you have to remember our rules about series circuits. For example, we know that in a series circuit that all those resistances are going to add up with each other because they all work to slow down the current that's coming through. And because they're all working together, so that means 3 plus 6 plus 9, I have a total resistance of 18 ohms. Now, going across over here, I can see that I can solve for the total current that's coming out of the battery. So I would use V equals IR. I is equal to V divided by R. This is the total voltage and total resistance. So that would be 24 volts divided by 18 ohms. And you can leave this as a fraction, or you could put it into decimal form. Either one is fine. And this will equal to 4/3 amps, or 1.33 amps. But what do we know about current inside a series circuit? Well, the current at one location is exactly the same as the current at any other location. So this might be 4/3 amps. That means these are all 4/3 amps. And then going back across again, I can solve for the potential difference and the power that's being used at each resistor. So V is equal to I times R. So I would get 4/3 amps times 3 ohms, which gives me 4 volts. Okay, so I know that over here this is 4 volts. If I work out over here, this would be 8 volts, and this would be 12 volts. Notice that all my potential differences add up back to the original battery value, and that's a good way to check your work. If I want to solve for power, power is equal to V times I. Again, you could either do this as a decimal or as a fraction, doesn't really matter. So P equals V times I. So if I start with, let's say, the bottom over here, I get 24 volts times 4/3 amps, and we get a total power of 32 watts. So now if I took the time to work through all those individual boxes, I would see that this would equal to 16 watts. This would equal to, let's see, 5.33 watts. And this would equal to 10.67 watts. Okay? So when I'm solving for all these things, if I go back to my original equation now, my original problem, I have the answer to all of these questions. What's the total resistance of the circuit? We solved that to be 18 ohms. How much current is passing through any point in the circuit? We solved that to be 4/3 amps. What is the potential drop at each resistor? We solved that to be 4 volts, 8 volts, and 12 volts. Okay? One other thing I would like to point out, now that we know the power, we could also solve for how much energy is used at any given moment using the formula work equals the power times time. So, for example, if I want to know how much energy was used up in a time of 2 minutes, then my work would equal to my total power of 32 watts times 120 seconds, and I would get an answer of 3,840 joules. Okay, that's a possible example question. Another possible question that they might ask is, which light bulb is the brightest? And you guys should always note that the brightest light bulb, assuming they are all light bulbs, is the one with the most power. In this case, the brightest light bulb would be the 16 watts because it has the most power. Even though it's the highest resistance, we'll talk about why this works out this way, but you're always going to talk about the brightest light bulb by looking at power.